I'm really excited about our next speaker. When we think about drones and UAVs, especially in recent years, there's obviously some very specific topics that come to mind. And most, if not all, of those conversations seem to be about things taking place on Earth. But I'm a little bit curious. These robots, especially the things that like VJ was showing us earlier today, they seem to be signaling the future. So I was wondering if maybe the road, or maybe it's skyway to where we are currently, might have a little bit more of an extraterrestrial element to it. Our next speaker has a long career leading robotics efforts for NASA, defense, and industry. And he currently serves as the co-investigator of the Mars Exploration Rover and the Mars Science Laboratory Sample Analysis at Mars Instrument. Here with some news from outer space, from the ultimate drones. Please welcome co-founder and chairman of New York's very own Honeybee Robotics, Stephan Gorevan.
Thank you very much. It's nice to be here. I am the co-founder of Honeybee Robotics, Spacecraft Mechanism Corporation, and was selected to the Mars Science Laboratory science team, also the Mars Exploration Rover science team, and I think that I'm not a drone expert, per se. On the other hand, we do have these amazing robotic ground devices on another planet. We have two that are operating right now, Opportunity, and today I'm going to talk about the Mars Science Laboratory, or as more commonly known, Curiosity. And in addition to being on a science team, my company provided two major electromechanical subsystems to the Curiosity rover, so Curiosity has been a very big part of my life. Briefly, I don't have much time to talk, so I'm not going to talk a lot about the science. I'm going to talk about the technology and more specifically about the instrumentation and sensors on board. Perhaps there's a hint here of what might be in store for drone technology and the expansion of the drone application envelope. But in brief, we've gone to Mars with these rovers, and in particular the MSL or Curiosity rover. We're looking for the biological potential of a region on Mars, specifically a place called Gale Crater. We're going to look at the history of the geology of the region with the payload. Water, research for water is very important, not only for whether or not there was life is on Mars presently or was in the past, but also for the prospect of people coming to Mars. And similarly, the radiation hazards are going to be investigated as well, because the radiation hazards are a danger that has to be explored fully before we send people to Mars. So there's a depiction of the rover. That's about the size of a Mini Cooper, and that robot arm there is about 7 feet long. It's a big machine. So as I said, I'm going to talk a little bit about the payload. Starting at about 9 o'clock, we have the DAN instrument, and it really is a sensational payload. Nothing like this has been on any other planetary surface before. DAN measures hydrogen, and the hydrogen that you see in this near subsurface is usually water. REMS is a weather station on Mars, and we can keep a very accurate track of the weather on Mars, the temperatures, ground temperature, air temperature, and winds. MassCam is a high-resolution device that can look far away or close and help rover planners decide where they're going to drive next. And similarly, the ChemCam gives the rover planners and the science team a first-order chemistry information about what the targets in the distance are composed of. And I mean fast. We can shoot a laser at 30 targets in one day, or as we say on Mars, one sol, and we can get a pretty in-depth chemical analysis of that target. So this helps us decide, us, the science team and the rover planners, where to drive the next day. RAD is the radiation experiment that not only looks at the radiation coming to the rover from space, but also the RAD was the only instrument that was turned on during the cruise to Mars, because the radiation environment of the cruise to Mars will be important for future astronauts that are going to go to Mars. The alpha proton X-ray spectrometer measures elemental chemistry of any target that it's placed on, and I mean literally placed on. The MALI is a wonderful high-resolution microscopic imager, and at the end of the arm, we also have, it's a crowded end of the arm, there's a drill, a scoop, a brush. I designed part of the brush, and various sieves, a sort of a sample processing system on board the end of the arm. And we need to process the samples for two instruments I'm going to mention in a second. Underneath the rover is the MARTI, which was a descent imager, which helped us locate where we are, and was important, very important for contextual information. And the big boys are CHEMIN, which is a X-ray diffraction device. I mean, if any of you are related to going into instrumentation, we have actually sent an X-ray diffraction machine to Mars. It's just amazing that it could be hardened and miniaturized to be able to do that. Again, this is measures. It determines the minerals of the target, the mineral composition of the target. And the big daddy is SAM, which is actually 3 instruments in one. And basically, SAM has the ability to analyze the atmosphere and look for organic compounds. A little bit more about the sampling system. The sampling system, again, it's a 7.5-foot arm, and at the end of the arm, you see there we have the MALI, the APXS, which I mentioned. Chimera is the processing system that sorts the scoop samples and the grindings from drilling into the appropriate sizes into inlets on the deck of the rover so that they can go into the CHEMIN or SAM instrument. And then there's the brush is also on the end of the arm. This is Gale Crater, 150 kilometers in diameter, going way out. And you can see a small landing ellipse there. That was about 6 kilometers, and there's a small dot in the middle, and we basically hit the bullseye. So I'm going to talk a little bit, show you a little bit of what each instrument does. And again, I think the hint here is how we might expand the application envelope for drones. I think we must be in the infancy of the instrumentation that we can put on drones. We haven't even scratched the surface, I don't think. So here's the descent imager showing the heat shield separating as we're heading to Mars. A marvelous photo. This is a picture taken about 3 meters off the surface. You can see we're actually kicking up dust from the last retrofire to slow us down as the Curiosity descended to the surface. ChemCam is up on the mast with the mast cam, and it actually shoots a laser and will make obliterate a small target, and we can do a spectrographic analysis of that puff of smoke that comes from that laser ablation, and we can do on Sol 13. As soon as we landed, we did 30 shots in one day, and we were able to do a rather detailed chemical analysis of a rock that we were interested in, and actually some rocks around it. It's the ability to work fast and to help decision making that night so that we can plan the next day what we're going to go and what we're going to do. Instruments work together. The ChemCam, along with the alpha proton X-ray spectrometer, which measures elements, detects elements, and the mass cam, were used on, for example, this target, Jake Matijevich, to determine that it is a basalt, very much like basalts found in the Mojave Desert. And this is just an example of what it could do. If you see a rock, it looks like basalt, but you can't tell if it's basalt unless you analyze it in depth. Here's a picture, a microscopic image of produced by the MALI instrument. There's its sampling deck on the upper left, where samples are placed for analysis, or the MALI can also look at targets in situ. And on the bottom left is the scoop at the end of the arm, of the Curiosity arm. CHEMIN, I mentioned, is a very sophisticated X-ray diffraction device. I mean, sophisticated for use on a planetary body, and other than the Earth. And it uses X-ray diffraction. In this case, we were able to determine a sample at a place called Rock Nest that was also a basalt, but we couldn't have done it. We couldn't have actually proved it was basalt. We couldn't prove on some of the targets on the previous rovers that they were rocks that we thought they were until we got the X-ray diffraction there. The REMS, the weather station, this measures daily temperature of the air, the ground, and the wind speeds and directions. Here we see on Sol 20 that if we move from the rover moved from gravel to bedrock, the temperature swings dropped, but they were still a wild swing from the morning to night of the ground temperature of 90 degrees centigrade. Mars is not a terribly friendly place yet. Also, unusually, the pressure drops by 10% a day on Mars. It's just incredible, and we were able to measure this with the REMS instrument. RAD measures the radiation coming to the rover at all times. At all times it's turned on. And it was on also during the cruise, and we were able to make very significant observations with respect to, as I said before, sending astronauts to Mars. And depending on who you talk to, it looks like it's going to be possible to send people there. They're not going to be fried by the time they get there. Dan, using a neutron bombardment, is able to tell how much hydrogen is in the near subsurface. And the hydrogen in the near subsurface is almost always due to the presence of H2O. And one of the discoveries that was just recently released is that there is much more water in the near subsurface, at least at Gale Crater, than we ever thought there could be. And that's good news for sending people to Mars, because water, it's not something you can only drink, but it provides fuel. Also on board is the, as I mentioned, the suite of instruments called SAM. SAM measures gas abundances in the air. As you can see there, we found out that nitrogen is not the second most common gas, argon is. And SAM, with a tunable laser spectrometer, a gas quadrupole spectrometer, and a gas chromatic F spectrometer, is able to measure organic compounds. And also one of the great big discoveries, and it was hard to get to it because we had a lot of interference with things that we thought we might have brought from the Earth, is that there do not appear to be methanogenic organisms, no little bugs that are excreting methane, at least not now at this time of the year and in this place. That doesn't mean that life is not on Mars necessarily. It's the prospect has gone down, but it also says nothing about past life on Mars. It doesn't say one way or the other not whether there was past life on Mars. This is a sort of a track to a place we just left called Yamaha Bay. The landing station, the Bradbury station, is on your left, and we're moving to a place called Mount Sharp, which is at the center of that crater. This is Yamaha Bay. It's kind of remarkable, except for some sparse vegetation. To me, that looks like so many places I've been to in the Mojave. You know, Mars is tens of millions of miles away, but you know, in interstellar distances, we rub shoulders with Mars. It's a very close relative, and I think that's why a lot of people, of course, believe that that life on Mars may have coexisted with the start of life on the Earth, or it may have come from Mars to the Earth, and so on. The brush is used because when we use the APXS and other instruments on the arm, if we just sent the APXS on the rock, it's good. A lot of the results will be of the dust, the aeolian wind-blown material that's going around Mars, and we don't want that, so we brushed the surface of the rock. An opportunity, we abraded the rock. We didn't abrade on MSL because the cost overruns, the abrader was cut from the payload. But we are reaching out and touching and manipulating Mars. We are also drilling, and the drilling is important because we are looking at material that's not been changed by the intense, long radiation bombardment of Mars. And if you look at the surface, one of the things that excited the science team was the surface is sort of red. And as soon as we drilled down just a few millimeters The material coming up was this gray color, meaning it hadn't been altered by the radiation. It was protected by the upper few millimeters of rock. And this is very exciting because we're able to get a look into the past that's not been obscured, not by this constant radiation bombardment. And right now, the rover is trekking to Mount Sharp, a 5-kilometer mountain at the center of the crater. It's going to be a spectacular trek. These are the foothills, just remarkable layers of canyons and buttes of Mount Sharp. And if you look closely, you can see the layers, and that's the key to why we want to go to Mount Sharp. The layers mean looking back into time. And on the Earth, when you see layered rock, it's usually sedimentary rock, and sedimentary rock is often associated with organic material. And to give you an idea of the size here, oh, that slide didn't work. It's supposed to be, there we go. There's a small boulder in that red dot that's the size of Curiosity. So the big one actually climbed Mount Sharp, and just investigating the layers. So that's my talk for today. Thank you.